about much either, which is kind of scary. And I'm going to go back all the way to 1930 and talk about what they learned back in 1930 to move air. And believe it or not, nothing friggin' has changed. What it took and what they understood to move air back in 1932 was in fact no different than what we need to know today. In the 1930s, we had gravity furnaces that worked by convection currents. They worked beautifully because the duct was big, it was smooth, it was short, it was fat. When we entered the 40s and 50s and we started to introduce fans into heating and cooling systems, the fans didn't have to be very powerful because we had a legacy of building good ductwork systems. So it was big, short, fat, and free-flowing because we came from a time when we had no fans at all and gravity had to do the job. So all that I'm going to do this morning in the hour and 15 minutes or so we have together is just go over some of the fundamental rules that you must have. And there's 3 that you have to follow. Number one, in making air flow through equipment properly is the duct has to be fairly big, but the thrust of my talk today is not on the size of it, but rather the fittings of the main trunk. How many different pieces of sheet metal change direction? I'm going to go into that in detail so you as a builder know what to look for. Number 2, if Mrs. Smith is cold in her bedroom in the winter or hot in the bedroom in the summer, what's the problem? It's probably because the branch is not big enough. And that's a whole different issue with design and installation of sheet metal, is getting the air to the bedroom. And lastly, I'm going to talk about duct leakage because it's a big, huge issue. So I'd like to present this information, which we started with 10 years ago in the Basics of Moving Air course. It's being developed right now in brand new one. We've redone the complete main manual. We're just now on the appendix. We'll do a beta run for this for hand-picked selected trades, which we'll do in the next 30 to 60 days. And we're welcoming input, welcoming names for people who would like to participate in a beta course at the trade level. And we should have this available to go throughout the province and in January and thereafter. My co-author is Gary Milligan. He's an A-fitter, gas fitter, contractor. His aerodynamics expertise is better than anyone I've ever met in the contracting business, and why I got involved in the development of this course 10 years ago. And he's right now reviewing the main manual along with his wife, who's a first-class, what do you call it, a grammaticist, someone who can speak proper like I can't do. And she's going to put it in English that people would like to read. I'm a president of Energy Products. I'm involved as a ventilation manufacturer and been involved in business for 37 years, member of CHBA for 35 years, and one of the founding members of TECA. So that's where I'm coming from. I'm in my 3rd career. My first career is I was a motorcycle mechanic. I did that for years. I then went on to work for engineering the BC Telephone Company in diesel gensets and controls. And the first job paid for my engineering degree at UBC, and then I've been self-employed now for the last just about 40 years. So we're in the process of revising this right now. I do sometimes love having a soapbox here of a captive audience that can't run out the door when I say something. My next 4 slides are from me personally, and they do not reflect the position of TECA or CHBA or its local association. So I want to build that disclaimer into things right up front. I'm very, very proud of my niece. Her brother is on the snowboard team for Canada. He competed in Sochi, Russia, and he's going to Seoul, Korea in February. And he's a very, very good snowboarder, and he's one of the best in the world. He's been on that team for 6 years. I have to hand it to her sister, however. My young niece is 32 years old. She was just about dead after a car ran over her when she was on her bicycle about 10 years ago. But she just came back. I picked her up at the airport from Switzerland. She flew from Zurich, came in on Tuesday night last week, and she's the first Canadian woman ever, the 7th woman overall, and the 100th to finish what is called a DECA. And you know how bad a triathlon is, which is what they used to call the Ironman. Well, try doing 10 of those things back to back nonstop until you drop dead. Well, she just finished one of those in Switzerland, and I'm just proud as hell of what she's accomplished. 38 kilometers of swim, Calgary and back on a friggin' bicycle, and Hope and back and Hope again to run. And she did that in 11 and a half days, which is well short by 3 days of the time allowance which she was permitted to complete the event. Absolutely unbelievable performance. And underneath it, just the nicest personality in the whole world. Just a wonderful person. I'm a nerd. I'm a proud nerd. I love technology. And I personally have been looking for the last 30 years at wrestling with this global warming carbon dioxide issue. I had the luxury of listening to an absolutely awesome conference that was presented in Phoenix, Arizona on December the 2nd to the 4th in Phoenix, which was on YouTube for free until Sunday at midnight. There were 15 scientists that spoke at that conference, and they were absolutely wonderful, wonderful people. They had risen to their pinnacle of their strength. One of them was Tim Ball, a PhD at the University of Manitoba. And he's basically saying that this is a quote from someone else actually, but his whole theme was on this. The global warming scam with the literally trillions of dollars behind it that has corrupted so many scientists and has carried the American Physical Society before it like a rogue wave is the greatest and most successful pseudoscientific fraud I've seen in my life as a physicist. This conference brought the best people in the world that all traveled to Phoenix for free to present the true science of what's going on in the world. I won't go with the other quotes. The second speaker that dropped me on my ass was this gentleman, William Haper. William Haper was a physicist at Princeton, one of the renowned universities in the United States, and he's now been named what is called an emeritus professor. And that means you're so freaking good at your game, you're allowed to carry the title of professor even in your retirement. And he presented a topic on the same thing. But what added a special credibility in my mind was the fact that he ran the Department of Energy Research Committee, a research group in the Department of Energy in the United States government, and he looked after everything to do with energy that wasn't military. This guy was extremely credible, and he just talked about the fact that for the last many years, 9,000 years, we've had temperatures in the world that have been 3 degrees C over where we are in the last 1,000. So we're just returning to a norm. The fact is the climate over the last few years did get warmer, and it was driven, number one, by cloud cover, which was 97% of the effect. 3% of the effect was carbon dioxide, but the big bull in the china shop was the activity of the sun. So my only reason for presenting this, I'm hoping that I can cause you guys to think a little for yourself. Don't believe the mainstream media, and if you want to learn any truth, be careful where you get your sources. The last thing was a gentleman, Richard Feynman, who was the gentleman that is a physicist, a Nobel Prize winner, and he was investigating the Challenger fiasco, the Challenger space shuttle when it blew up, because they knew NASA could not do an internal investigation. It's sort of like police investigating police. You don't ever get any good results. They brought someone outside that was a world-renowned physicist to analyze the failure and get to the bottom of the actual cause. His made a comment was that I think is extremely appropriate. It was quoted by Bill Ball. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the data, it's wrong. And this quote applies to the theory of man-made global warming. So if you want to get into that, I'll talk about it in the future, but that's all for my soapbox for the moment. Back to physics. My message this morning is very, very simple. Some things have changed in single-family homes. Many things have not changed, and facts remain the same, well, until the last U.S. election, ignoring alternate facts. And the article that was mentioned at the conference is kind of fun. If you have a half-truth and a half-truth, what do you really got? 2 half-truths, my wife said, although one could imply you half-truth and a half-truth is the full truth, which of course is crap. Did any of you hear me present at the Hilton with the HPO last February, 10 months ago in February? Okay, so this information is new for you. I have 56 slides. I'm only going to bore you with 10 with text. The rest has got pictures of real live shit on it. And I got an 8-second video, which if everything works right, should work. And I present this in cooperation with Gary Milligan, who's busy making a buck today out on the job. But one of the reasons that I thought I'd bring this next slide up is because Ken Connolly was a builder in Nanaimo. Have any of you guys from Nanaimo? No one's from Nanaimo. Ken Connolly's been building in Nanaimo for many, many years under the name of Pheasant Homes. He took the POMA course, Principles of Moving Air, Quiet and Efficiency, about 7 or 8 years ago, And I called him up on Thursday and asked him, what can I tell builders today, as I'm speaking to you, what he learned during that course? His comments are real simple. I use this information in every house that I build. The movement of air in houses is important. And I now better understand the HVAC choices that my sub presents to me. In fact, and I think you'll see at the end of this, his comment about not trying to save 25 to 20 bucks on fittings is very, very important advice. Planning, I reduce chopped up framing. No builder who builds well, who loves to frame, who loves to see a good frame, wants to see the frame chopped up. With a little bit of a framing, a little bit of planning, you can avoid damage to your structure that you took pride in building. And it overcomes the last-minute shoehorning of equipment, which is a problem we face every day. It's trying to stuff a water tank, a furnace, and all the controls, distribution, all into a room that's way, way too small for it to start with, and only made worse when the rule of the game on the construction sites, the first person that gets access to that room basically controls it, and anyone else second then is on the hind tip. It reduces the drops in back framing, and the homeowner likes it because if you put in a system properly, it's quiet. And today, quiet is important because noise is just one of the stresses that we need to avoid when we're living in a house. The changes to housing, though, however, are extremely subtle. Have you ever thought about building a 3-floor house and what happens? We've been able to electric baseboard heat the top floor of 3-floor houses for the last 30 years. And do you know why you get away with it? It's really, really simple. Up until the last 7 or 8 years, we didn't have second-tier electricity, so it was not stupid to heat with electricity. But the problem is when you build a leaky house, remember, your thermostat is the only thing that the furnace listens to. If you have a thermostat here, this is the captain of the ship. That furnace will do anything in its power to maintain this furnace thermostat satisfied. It has no idea what's going on in the basement, has no idea what's going on in the bedrooms overhead. When you have a standard build house, your top floor is getting a free ride off the air that's exfiltrating from the top floor because it's getting a free ride on the furnace heating the main level. The price, however, is paid, and it's a bitch to make basements comfortable because that's the pond into which infiltration air sits. It sits on the floor. And there's a million discussions around the table how to make a basement comfortable when a good part of a basement discomforting is that the building is so damn leaky, it's the pond for which infiltration air will settle. If you build a leaky house, you get a free ride on the top floor, but it comes with a price. That is changing today, and that if any of you people built under the R2000 program, have you ever been burned with a top floor that doesn't heat adequately, which is the natural result of building a house that's airtight because you don't get the heat on the main level getting you a free ride upstairs. Your top floor needs heat just as much as the main. In fact, it's worse than that. I'll get into it. No longer can you stuff your air conditioning, your heating, and your ventilating, and your air conditioning equipment in the attic unless you pony up with a hell of a lot of money to your spray foam contractors to insulate the attic roof system. And lastly, the interior designers are making life almost impossible today as a heating contractor, and we appeal to you on our knees to hammer those people and tell them we need space to do a proper job to install heating and ventilating, because if they want their house to work, they bloody well better give you space to give to us so that we can serve you properly. It doesn't work any other way. What to do? I believe today there's 2 things that we can do. Number 1, at TECA, our job is to provide the best education that we can to our contractors so they're up to date, hence the 4 courses that we're abbreviating for purposes of your benefit today. The other hand, however, is that you are our partners in building a house that's proper, and if we work together, we'll end up with a better house for Mrs. Smith, because ultimately, Mrs. Smith, which is our fictitious homeowner in my talk, ultimately, she's paying your paycheck, and she sure as hell is paying mine. So what do? You could be asleep, and this is unfortunately what's happened after the last 20, 30 years. The builders traditionally in this province have ignored the details of heating and ventilating, in part because we haven't brought this to you in a forum such as this, But you have been able to lean on the sub and ask them to do it, but no longer is that possible. There are too many choices, and that sub needs your input to do his job properly. It's got to be. Facts, and unless you believe in alternate facts, these don't change. Have you ever thought about the fact that the heat loss on the top floor of a 3-level house actually exceeds that of the main level? It does, because the top floor has got 4 walls that's full of windows, and it's got an attic, and the attic has got a heat loss into it. Otherwise, you wouldn't put any insulation up there. So it's got one more cold surface than does the main level, which is buffered from outdoors by the top floor and buffered from the basement. So here we have a top floor today that has more heating requirements than the main. And I'll get into it more later, but the bottom floor, the basement, has even lower losses again because it's buffered from the outdoors by the dirt which surrounds it. Also, we have the heat gain into the top floor is the greatest. Any of you guys take bitches and complaints this last month of overheated top floors from past customers? The top floor takes the hit from the windows that are exposed, and you have less shrouding from your neighborhood house and your trees on the top floor on the west when the sun comes in at a low angle than you do in the main. But you're also heating your top floor from your attic. So your attic has a higher heat load, just like as your top floor has a higher heat load, just like it has a higher cooling load than does the main level. We've also got to the point now where our heating appliances have more throughput than ever before in history, and I'm going to focus on this because it has a huge impact for you and the subs that you work with. I'd like to bring to your attention that it costs money to move air. Scott's point, you can move water more efficiently. Well, I'll concede that argument, but I'll beat him up on most of the rest. It costs money to move air, but what I am going to show you, though, that the cost of moving air is in part because we're strangling the ductwork systems and we're causing ourselves to use the 3/4 horsepower motor he's suggesting, is because in ignorance we don't realize that the cost of moving air is only partly dictated by how much efficiency you bought in the motor. The biggest part of your electrical cost of moving air is the ductwork, which you're asking that fan to push the air through. Lastly is, if you have duct leakage, and I'm going to spend some time on that, if you've got to deliver 50 cubic feet of air to Mrs. Smith in the bedroom to keep her cool, and your system has 10% leakage, you have to wind up on that fan motor to get that same 50 to her bedroom. You're going to spend 33% more in electricity to do the job. For a 10% stinking loss of leakage, you got a 10% hit in the cost of moving the air to ramp up that motor to bring her back to what your design point was. The practical results of these changes and rediscovered facts are: we locate the HVAC system in the basement. In most cases, the few exceptions are in the top floor where you're willing to reduce your installation cost and accept a bit of noise having equipment right beside bedrooms, which is a risky stunt to pull, but you can put your ductwork in the attic if you seal it and insulate over to the R value of your wall. You will meet 936 in doing that, but there are some risks in taking that choice. So by and large, you're putting your equipment in the basement, and yet your load is in the greatest distance, apart from that which is top floor. And of course, your interior designer has got so frigging few walls on the main level that this house is 1 inch away from seismic disaster, forgetting about the fact you left no walls to get your duct from the basement up into the top floor joist system. Okay, you knew I was going to be opinionated, I suspect, by my first few comments. But I welcome any kind of challenge technically on what I say, because I'm wide open to questions or challenge to any of these things, because they come with a lot of years of thought, and sticking my neck out like this because I relish the challenge. I'd like to soapbox for a minute on F280. There are many people out there in the provincial government, HPO, and other places right now that are telling HPO, or telling you as builders, that the F280 is the best thing since sliced bread. Basically, most of the time it comes from government. It's crock anyway, but there are some strengths to what they say. F280, 2012, as Scott claimed and mentioned properly, is the most recent standard, most recent updating of that standard. It was chaired by a friend of mine, Gord Cook. There are two things about this standard that make it more precise to do a heat loss program in your house than ever before. And they're really frigging simple that I don't have to get into math to explain. The Alberta infiltration model is a fancy word to tell you that if you're doing a room-by-room heat loss and you calculate the R value of your windows and your walls and all that kind of stuff, would you expect that a room in the basement would have just as many BTUs of loss as the same square footage room with the same wall, the same window if it was on the top floor? It's a trick question. Would you expect the two rooms to have the same loss? We've assumed that to be the case, but what these guys are suggesting is that ain't the case. Because what happens is you guys being here probably have already had enough building science information to know that in the wintertime, the stratification that we always talk about and the discomfort that it brings in the basement is not what we call a static event. It's a dynamic event, which means to say your furnace runs to keep the thermostat at 72 degrees, 5 feet off the floor in the main level. This furnace does not know what's going on in the basement, doesn't know what's going upstairs, because there's an ongoing in current at the basement, and rising of warm air, and exfiltration at the top. The result is this is a dynamic event, and the strength of that change is driven directly by the height of the house and how cold it is outside. Where I'm getting with this, the Alberta infiltration model magically corrects for this factor, and it will assign a greater heat loss to your basement room, with all else being equal, than the top floor room. And that additional padding of the heat loss in the basement is affected by the input to the leakage rate that you're going to put into the software program. So it's quite beautiful. It tells you that you're going to need more loss in the base of a leaky house and less loss from the top floor in a leaky house, where they tend to become uniform if you input a tight house. That's what that means in simple language. The next one was a G.P. Matillas. Way back in 1980, when I got involved with this stuff, he made some really, really, really interesting discoveries. Here's, for example, if you build a slab-on-grade building, it's a slab-on-grade, single-level house, Scott very correctly pointed out there's massive heat losses to the perimeter of this slab, because concrete is a beautiful conductor. An 8-inch concrete wall is R1. What's the R value of a double glazed window? 2. Triple glazed, 3. Throw in argon and low E, it's maybe 4. Concrete, R value is 1. If you have a radiant heated slab, or even a house that's got no radiant heat, that slab edge is losing massive amounts of heat to the outside. Okay, what this guy Matillas said, though, he was really a smart dude, because he was a common sense guy, one of these guys that I really admired. And what he said is the more you put that slab into the ground, you go deeper and deeper and deeper, and you make it into a crawl space slab, and you go deeper and deeper and deeper, make it into a basement slab, those edge losses become less and less and less again, because you were buffered from the outdoor conditions by how much depth that slab is below the grade. Well, what this guy is also saying is that the heat loss of that basement wall above grade is horrifically high, because that above grade wall is seeing the outdoor wind. As you get cold, down and down and down, the losses per square foot go down and down to the point where you get into the center of the basement floor, and there's zero losses. The path between the center of the basement floor and underneath the basement slab is so great to the outside, the losses are zero. They just don't even add up. You ask yourself, why the hell should we put R12 underneath the slab? Well, I'll get onto that in a minute. Okay, if you decide to use F280, and I would seriously discouraging you from using this F280. Why? Because it's basically looking for precision, which you can achieve in a world that isn't precise. To give you an example, if you're building a house, are you able to build the R value that was set on the plan set? Maybe yes, maybe not. But what about thermal bridges? Unless you've seen a house in an infrared camera in the middle of winter, you probably don't have a clue what's thermal bridging. I personally made a study of that because I've done indoor swimming pools for 30 years. And what happens if you've got a thermal bridge? Condensation. Anytime you see a steel post and steel beams used in an indoor swimming pool, run like hell. Thermal bridges have massive losses. And you don't insulate thermal bridges, you thermally break them, which is a different animal than insulation. Insulation at R20, R30 is good shit. but you thermal break with a lousy 1/2 inch or 5/8 of an inch of Donna board, like Scott was saying, in the slab edge. Your surface areas are small. The R value doesn't matter. You're thermally breaking it. So in your mind, remember, you differentiate between thermal bridge and thermal bridge protection and R values. They're different animals. Number 3, is the air tightness of your building what you sold or what you thought it was, or are you actually testing it? Because if you don't test it, it may be a hell of a lot leakier than what you think, because in the lower mainland, we get away with bloody murder here because our climate's mild enough. Mrs. Smith isn't quite as pissed as she'd be if you built the Vancouver house and tried to heat the sucker in Prince George. Number 4, why should you not follow F280 2012? Because what we've done in the past is our industry has buffered you by a safety margin of about 50%. If you start to engineer to what's called this brand new government buzzword called right-sizing, which I believe in if you're a scientist, but it's got a big, huge problem, because if you right-size and you calculate that you need 5,000 BTUs to a room, and your heating system isn't precisely divided up to a great degree of precision, you aren't going to make any corrections at the last, because you right-size this thing with equipment that's just big enough to do the job and a ductwork that's just big enough and a branch just big enough. You're going to get royally screwed over, because this industry and this building industry isn't ready for that level of thinking right now. So be careful. Have you met your customers' expectations of response time? Mrs. Smith today, for right or wrong, is going to demand pickup. Now, the precise answer Scott and I will give you if you ask how much heat in your home is the answer you probably haven't heard. And that is, in January the 21st, coldest day of the year, guarantee it, I checked the almanac, it is going to be minus 10 C, and your furnace theoretically should run nonstop 24 hours a day and squeak you to 22 degrees inside while it's offsetting that outside. And that's what F280 is going to give you. Is Mrs. Smith going to be happy if she goes to Whistler for the weekend and comes back and realizes the house doesn't pick up? Because you got 0 left over. And just for laughs, if you look at F280 really, really closely, you'll find out that the BC Building Code requirement for putting R12 underneath a slab is absolute stupid economic waste in a basement situation in the center. It can be justified for the outside 2 feet up to the outside perimeter wall, getting thicker and thicker insulation as you go up, but you can't justify insulation in the center of the slab because there's no economic merits for doing it, but it's in the code just because no one gave any serious thought to it. The only rationale for insulation underneath is you got really, really wet soil and water moving underneath it, sucking the heat out. So if I was building in Richmond, I'd do that. If I was building somewhere dry, it's a friggin' waste of money. But that's just a comment from myself. Haven't helped me. I'd like to go back to 1932. A good friend of mine runs a company in Abbotsford. Floyd Peterson runs G.P. Peterson, his son. He's an absolute hog for old antique stuff. He gave me this book, and I thought it was really good. You know, that book is 80 years old. You open up the book, and holy shit, it's the same thing we're teaching today. Quite amazing. If you got a heating contractor, it's a tradesman in sheet metal, red seal sheet metal contractor, he's more than 50 years old, he probably knows this shit. If he's been through the schools since then, it's all been culled out because they spend so much time learning how to make fittings you can make cheaper at Echo and not teaching what's important. It's unfortunate. So what happens is, if you go in and take a look at the old book, you take a look at an 8-inch duct by a 30-inch duct, and it says the equivalent was 16 inches around, 16.4 inches. You take a look at the new book, give or take a quarter of an inch, it's the same thing. The bottom line is nothing's changed in subsonic aviation for 80 years. All we're trying to do with our course is bring people up to where the knowledge existed in 1932. The only thing different is the ASHRAE used to be called American Society of Heating and Ventilating Engineers, and I'm kind of pissed because I'm a ventilation guy, and I'm kind of pissed that the refrigeration guys took the V out way back in about 1940 when air conditioning became the be-all and end-all, and ventilation became a diminished interest. Ventilation was driven in schools in the 1920s and 1930s because of disease transfer in school kids. I couldn't resist. To a good sheet metal contractor, walking through a brand new home today and looking at the sheet metal that goes into new construction is as bad as an aircraft engineer thinking he's going to get off the water with that beaver. Essentially, 10% of the people out in the province today that are sheet metal workers do smash-up good job, 60% get away with it barely, and 10% are disgraced and would love to kick their butts right out of the industry. I'm going to speak then on 3 things that you as builders can look for and do something about on the next time you award a heating contract. And I'm going to speak about restrictions and fittings. And basically, restrictions and fittings are all dictated by the throat, the inside curve of a fitting. And I'll get to the science that explains that. I'm also going to talk about leakage. And the reason I'm going to talk about leakage is because it's absolutely horrifying when you look at what goes on in our industry. This is a good quality sheet metal elbow, capped off here. It's got a hole in it here. And I can sit and breathe through the leaks in this adjustable elbow as if this elbow was not even here. And you put 50 of these in a house. So just guess how much you're getting out of the end. Bugger all. A lot less than you think. In the course of we built, called The Principles of Moving Air, we decide the only way to reach the trade in a credible fashion is build a model. We built a model at 1/10 scale, and we have on the left here 7 different fittings that you will commonly see at the base of a furnace when the cold air return comes down, makes a corner of the furnace. We have 6 different versions of that. 1, 2, 3, 4, 5, 6. 3 different on the supply air side, so we can actually demonstrate hands-on in reduced scale exactly what happens with the choice of fittings. We took this down to Boston. 550 people showed up at a conference Joe Stiebrick organized. It just dropped them on their ass. This is not thought about anywhere in North America today. So simple. Okay, so what do we do? What are the principal rules for moving air quietly and efficiently? Well, number 1, we want to keep Mrs. Smith's equipment happy. And I'm going to speak about that at length because if you don't keep the equipment happy, nothing else matters. We want to keep Mrs. Smith happy, and basically she doesn't care about the equipment. She wants to have good response. She wants to have a conditioned, comfortable room, and she didn't want to be noised to death with noise from the duct or from the equipment. And you can keep your sub happy if you plan ahead and make a little bit of space for the equipment and the ductwork. Those are the basic rules, and we're going to get into subdividing those in what we hope will be an implementable manner. I mentioned the ductwork systems then. There are 2 areas of concern to do with the duct. Number 1 is the trunk ducts, and number 2 is the branch ducts. Then, of course, leakage. What is a trunk duct? A trunk duct is the duct that usually goes the full length of the house. It's usually the big stuff, and it's defined as a duct that's big enough it's got branches coming off it. So when you see a branch coming off the side or top of a rectangular duct in the basement or a crawl space, that big thing is called a trunk duct, and there's 2 parts. There's a cold part and there's a hot part. From the trunk, then we have what are called branches, and I'd like to show you about 10 slides to show you about trunk ducts. What is the problem the trunk ducts cause? If they're undersized or they're badly designed, you get equipment and excessive air noise. And I'm sure lots of you have heard of air noise problems. The sleeper, however, is filter life. Every piece of equipment on the market today has what's called a sweet spot. It's a sweet spot where it moves the right amount of air to take the heat or cold off the appliance. And if you don't move enough, the equipment is not happy. And what happens is that equipment has got a certain degree of what we call static pressure capability, which overcomes the resistance of the duct that we have installed on that furnace. The problem is the furnace doesn't know the difference between the static pressure that's created by the ductwork and the grills and everything else, and it looks on top of that, the filter is also additional static resistance. So if you have a ductwork system that's really horrible and has high degree of resistance, and then you put a filter on top, you can't get any degree of filter life out because it barely starts to get dirty, then you got to turf it. This was okay in the days of horsehair filters and fiberglass filters, but when Miss Smith wants a better filter, it means to say she's only able to skim the top 10% off her filter before you're at risk now of high limiting that appliance for inadequate airflow over it. So essentially it shortens the filter's life way below that the manufacturer has rated it for. Heat pumps, compressor failures. Heat pumps are special animals, and I'll talk about them in a few minutes. The issue is with heat pumps is they're very, very air sensitive. EMCO, one of the larger distributors right now in the lower mainland, in fact all of BC, for heat pumps has a very good warranty program, but they've slammed the brakes on misuse of the warranty. If you take the compressor out because it's failed and you send it, they send it down to Tyler, Texas, the techs take it apart, and they can see by taking it apart whether that's seen what we call a high head pressure condition. And a high head pressure condition will often result from inadequate ductwork, because if you can't take the heat or the cool off your indoor unit, that thing works harder and it can destroy itself in the pursuit. Okay, well, no sweat at all, that's the sub's responsibility, but it's going to end up biting you in the ass, because if you smoke a compressor, you contaminate the refrigerant system which it's operating in. And it's a hell of a lot of work with a good tech to clean that system out so you don't smoke the next compressor as subsequent failures. So if you're using heat pumps, be damn sure you've got a good ductwork person on the job, and I'll show you what happens when you don't. Gas furnaces, on the other hand, are very, very forgiving. You wouldn't believe the crap and abuse that you can give a gas furnace and won't crap out. Amazingly forgiving appliance. But you will pay for it with gas waste. You will pay for it with a shorter venter life, because the venter is ventilating out to the outside of the exhaust products. If you're not taking heat off in the furnace, where is it going to go? It's going out through the vent system. And your venter motor will be a shorter life for that reason. And lastly, if you end up putting restrictions on your duct system, you'll be wasting electricity. And right now, contrary to Scott's claim, our electricity is worse than his quote. Delivered to my doorstep right now is 13 cents. 8 cents on the first tier, 13 on the second. We have to understand, before we go 1 inch further, what is air? That thing there is a cubic foot. It has weight. It has viscosity. It has momentum. It has all the properties of air. It's just a hell of a lot lighter, and we think it doesn't weigh anything, which is complete crap. Our heating systems today are having to move between 50 pounds and 200 pounds per minute to do the job. If you were doing that with a shovel and a wheelbarrow, you'd be bagged in 2 minutes. Well, furnaces today have what we call a proper heat rise. An installed furnace will have a cold air return that comes back at 72 degrees Fahrenheit. It goes down that corner band through the filter, goes through this fan, it goes up through the appliance, and the temperature difference between B and A is what we call the temperature rise of that appliance. Every appliance has a sweet spot. And I'm going to talk about that because it's a direct impact to you as builders. Every appliance has a sweet spot. You operate out of the sweet spot, you pay. This is a very, very simple chart, but I like to compare the old furnace with the new furnace because I think it shows something that's very, very important. The old furnaces ran what we call 70 degrees to 90 degrees Fahrenheit above that of return temperature. In other words, the cat is probably not going to sit on your supply grills because it's going to fry its toes with 140 to 160 degree delivery air. Now, maybe it was 5 degrees, 10 degrees cooler because there's a certain degree of conducted losses between the appliance and the bedroom, but nevertheless, this air was delivered at a very, very warm temperature, and that's where the appliance was designed to operate. That was designed in, that was standard. You take a look at a gas furnace today, the new high-efficiency ones, the cheapest, fastest way for the manufacturer to meet the mandated efficiency requirements on furnaces is to put a big honking blower in the cabinet, because if you sweep a lot more air through it, you can scrub off more heat, and indirectly you're meeting your efficiency requirements. On the same way, if you stand out on a cold winter day, the more the wind blows, the more it's stripping heat off your body. We do the same thing with a fan and a furnace. The heat pump, however, is a very magic device. It gets something for nothing, which is friggin' amazing in the laws of physics. But look what it does. It's operating at a temperature that's so friggin' low that if you're a retired person and you don't know about a heat pump, he's going to bitch and complain to the installer that this thing is air conditioning in January, because that's how it feels with 100-degree air blowing over you if the grill's right underneath your favorite TV chair. Well, remember this now, and let's switch to the next slide, because this is the crux of the whole thing. Right now, if you have a gas furnace, it took approximately 12 cubic feet to carry 1,000 BTUs. Everything in our business is BTUs. 12 cubic foot packs a huge amount of punch because it's hot. But you take a look at a heat pump today, these things here take 30 cubic feet per minute to carry the same degree of heat. So anyone today who puts this furnace and this duct system, or heaven forbid, this heat pump and that duct system, is a friggin' idiot. Is that commonly done? Damn right, because people are gullible and our industry isn't as smart as we should be. Let's get into more specifics, because this is down to earth for real world. The black furnace is Airco. It had the bulk of all the market here in BC because it was a damn good product. Efficient, quiet, reliable. There's probably thousands of these still operating right now all over BC. This thing here had 68,000 BTU, which is the model that I chose for this illustration, and it moved 730 cubic feet a minute, which was its sweet spot, and it had a little wee motor in it, which is all it took to do the job. And these ran at low pressure because this is an era when this brochure was created, we were coming off gravity systems, and we're putting furnaces into really big ductwork systems. Now, let's look at the red outline, which represents a Lennox furnace today. Again, it has 60% of the market share in BC. It's a good product. But look at, for the same output, it has 1,257 cubic feet a minute, which is its sweet spot, which is a hell of a lot more air than what we had in the old appliance. And this appliance, 72% more air, but the cabinet size is shrunk by 30%. So the logical answer, if the cabinet's smaller, let's put smaller ductwork on it. Wrong-o. In fact, if you really want to be an idiot, you can buy the same cabinet shape up to 135,000 BTUs. So the cabinet shape now today has nothing whatever to do with the BTUs that's stuffed inside. The reason they can make them so small, because you as builders have said to the furnace manufacturer, we want smaller and smaller and smaller appliances. The manufacturer's bent over, and they've done all sorts of stupid engineering, but they've able to achieve the 30, the 80, 95% efficiency, and they've done it with brute force use of electricity, which is not measured in the efficiency claims. Another crock that you've been fed. Let's look at this in more detail again. We have the black furnace outlined here. We have the red furnace outlined here, and we have the differences in green. We have 172% the air, 72% more. The pressures we have to run if you swap the new for the old is 3 times the pressure that you have to overcome to do the job, and your horsepower has gone up by 5 times in order to make that thing work. But don't worry about it, we don't count electricity in the efficiency game. I mean, once you start opening your mind to this shit, maybe if I wasn't raised by 2 friggin' scientists in my parents' life, I wouldn't be so critical. But this stuff is so glaring, it makes me pissed off.
Tell us what you really think.
Yeah, exactly. Okay, well, let's just put this back on the even keel here for a minute. We got to have this base so that you leave here with some simple, common sense schmuck message. That's how I live my life. We have speed limits in our game. You go through a school zone, a little bit over the speed limit, it's $170. I just paid one of them. 100 speed limits in school zones used to be 15 miles an hour, maybe it's 20, I don't know what the metric is. Well, we have speed limits in our trunk ducts. You can't go more than 12 miles an hour because that's the upper limit of speed in our trunk ducts. And a trunk duct is generally, you can have a little bit higher speed than a trunk duct for 2 reasons. A big duct is aerodynamically more efficient than a small duct. It has more square inches for its wetted surface area, all that kind of shit. But the branch duct, you can't get those speeds because you're right under Mrs. Smith's nose and right underneath her ears, so we have speed limits on the branch duct that's 5 miles an hour. You cannot exceed these speed limits, but they're being exceeded all the time. But again, to put things in perspective, if you're doing a Boston Marathon right now, you're running something in the order, depending on whether you're men or women, between 12 and 13 miles an hour. The classification that we do HVAC is what's called low velocity classification. It's basically 2,000 feet a minute, which is around 23 miles an hour. If you have a high-V system, they're very, very special. They're letting it higher, and those are proprietary designs by the manufacturer. And if you've got a central vac system or dust collection in your table saw, you're running 50 miles an hour, because what happens if you run less than 50 miles an hour in a dust collection system? Plugs up. The sawdust settles out, it's plugged up, right? So everything has speed limits. You cannot exceed these speed limits, you will have problems. Well, what does this mean in the builder's world? Well, what we use universally now throughout all of North America to move air through heating and ventilating systems are what are called double inlet forward inclined blowers. Forward inclined means if I got a snowball in my hand and I throw it like this, I'm forward cupping my hand. That is the direction that all these fans work for every product that's heating and cooling in North America. It's called double inlet because air can come from both sides, and it's got a very heavy gauge steel divider between the two because that gives you a very, very rigid wheel, which you can put right onto the motor shaft. It saves you a bunch of belts and pulleys and jack shafts and shit, and you end up with a package that's extremely compact. The manufacturers love this package because it's really, really small to get into the appliance that you've demanded that become small. And the other good thing about it is when you stick the motor right in the inlet, it has a huge degree of cooling, because the only thing that limits blower life today, short of stupidity, is overheated bearings. And overheated bearings are when your motor overheats, and overheating can be avoided to a large degree by the packaging configuration right now, which is thermally superb. The problem with this package is, on this back side, you have a full opening. What happened to that side? You've lost half of your area to do it. So what do you do to overcome those sins? More power. This is North America. We can solve all the problems. Bolt on more power. In preparing the course, Gary and I wanted to make sure that this was very, very well grounded. So what we did is we measured piles and piles of furnaces for all the important parameters. Return air temperatures, supply air temperatures, pressures, ammeter gauges, so you can find out exactly what's happening. There's absolutely no guesswork, and guess what we learned? Everything the textbook said in 1932 was in fact correct. Nothing's changed. One thing that I want to focus your mind on totally today, because this is a screw up that I've seen for 37 years all over BC. This single fitting, which I've labeled as a pig because there are worse, this single fitting changes the air 190-degree turn. The net result is that this air making this 90-degree turn thinks it's gone 50 feet of straight duct in that one single turn. That's the same as moving the furnace 50 feet away from what would be its ideal central location, and that's what that single fitting does. But let's go back to 1932 and understand the physics of what's actually happening, because our trade hasn't clued into the fact that this is important. In 1930s, the Tuttle and Bailey Company built a plexiglass duct of the shape I showed before, and it was clear, and they put soap bubbles in there, and they had a strobe photograph. And here's what they showed. This, by the way, is what I'm representing right now, which is the cold air return of most basement houses. Air comes down from the ceiling, makes this corner, and this outlined area is what I'm presenting here. The furnace fan here is actually oriented the other way with the inlet here, and this is the hot air delivery, and this is the connection. This has three problems associated with it. When the air is down this far, the air is more or less clean. It's what we call streamlined air, because it's so far from the disturbance above, it's had to straighten its act together and get all clean and straight. So you can see it's represented by the streamlines being quite clean. This strobe, however, is a big, huge, serious problem. It's a little bit like the Roadrunner cartoon. He's already over the cliff before he's figured out he's over the cliff. Well, this triggers all sorts of vortices. This is where the 50 feet of equivalent length comes from, is we've seriously restricted the airflow by pounding past this one fitting. But that ain't nothing. There's a double, triple whammy in this stupidity. Where do we put the filter? Right here. What happens to the filter? Only the bottom half gets any air through it. What is the velocity of the air going through the filter? Twice the velocity in half the area. What happens to the pressure drop of the filter? When it's clean, it's 4 times that which the manufacturers claimed it to be. Does it matter? If you sell doormats for filters, it matters not at all. The moment you upgrade to something that's actually doing some good for human respiratory particle sizes, this becomes a huge issue because the pressure drop is higher the finer you get, and this is complete destroying ability of the filter to do its job, and you're causing its life to be shortened to perhaps a quarter or a tenth of its regular life. But it's even worse than that. When the air comes out of this fitting and it's going into that double inlet blower, some of the air is going to enter right into the blower, but a good part of it has to come all the way around inside of the other side of the blower This fitting here is the most destructive fitting existing, and it's universal throughout this province today. And by spending a couple $300 on that one fitting, you can overcome many, many of these sins and put proper filters in at the same time. To give you a case and study, my sister had a brand new house built in Bridge Lake. Anyone know where Bridge Lake is? You know where 100 Mile House is? Just east of 100 Mile House, you're up on a 4,000-foot plateau. Cold as hell, Sheridan Lake, Bridge Lake, Interlakes. Well, there's nothing out there that you can heat your house with other than wood or electricity, and you know what I think about electricity. There's no gas, and oil's off the picture. So I recommend they put in a heat pump, and they put in a Mitsubishi, because I advised them that would do a good job in cold weather, and its specs, in fact, surpass that of any of its competitors in what it can do at 20 below. So what do we get? We get a heat pump. We get a sharp throat. Return on our outside heel radius makes no difference at all. In fact, it's a handicap. Filter rate where it shouldn't be. I walked in there because I had a commercial interest in the ventilation system, and I said, Mr. Contractor, please humor me. Take a few statics for me. I want one in this cabinet, one right here, just to find out if this duct system's going to work. Anyway, he says, screw off. I'm not going to listen to you. Basically, this is the way the sub always does it. This is after recommending to this builder 2 good quality red seal sheet metal workers who could do a proper job of a heat pump, which is air sensitive equipment. So he went to the plumber, because that's his regular trade, who's completely incompetent. I finally got pissed, called my friend who ran Mitsubishi here, and I said, can you apply some pressure? They lost their shirt in this job because this didn't even meet the manufacturer's installation minimums. It's a 3-ton piece of equipment. You can't come in on one side. The manufacturer didn't permit it. They had to lift the thing up, come into the side, and the bottom put the filter where it should have been, because that's the only way that compressor is going to live. I mean, I shouldn't have to do this kind of shit. You could put turning vanes in it. It's a good idea. A turning vane is real simple, a couple $100. You put a turning vane in here, and then this throat only causes damage to the airflow in the distance between the throat and that first vane. And see what it does? It drops you down to 6 equivalent feet, which is an 88% saving on the worst hole fitting in the house. If you don't leave here with nothing more than putting a turning vane in that fitting on your next job, you'll pay for your time here. That's what a turning vane looks like. You buy these things from Echo that sells Duradyne. Their rails are sold up in a coil, unrolled and flat. You roll these up, stick them in these little recurves, tap them into place, spot weld that in, and you just saved yourself 88% of the pressure drop, and you've horribly extended your filter life if you did it there. Any of you come from Salmon Arm, Kamloops area? No. Lou Sheet Metal has been running sheet metal up there. He's a red seal sheet metal worker. He's been doing heating in Salmon Arm for years and years and years. This is what he did in the house I was last saw him in. Everything that you could ask for is done right. A 3-ton heat pump, a massively large radius throat, wheel, turning vanes, filter where it should be. Filters are rated for the air to hit them square on. They're not rated to go in adverse conditions. He's got a tapered fitting at the top because air doesn't want to enter a sharp throat square fitting. Flex connector, so he's isolating his structure from his appliance. He's sound lined out as well. I mean, everything you could ask for has been done right, and I bet he didn't spend more than $500 to do it right. And he's knocked his pressure drop on this system to probably a third of what his competitors would have done. This guy's got balls, and I'd like to show you one case study before I put it into this particular discussion. He went into the Langley Home Show about 2013, 4 years ago, and he set up 2 identical furnaces. I really have to hand it to him. He did it well. David Hoare from Midtown. Furnace A, furnace B, bad, good. He put these gauges on here so that we could set these furnaces up so there's absolutely equal amount of air coming through both. So they've been finessed to be perfect twins. What he had here was a 1-inch filter with standard mounted, sharp throat, standard return, everything was normal, radius throat, turning vanes, and a big filter. And these gauges here show what happened in getting air from here 3 feet away, actually inside the appliance. That's how the appliance sees it. How hard did it have to work to do the job? My photographs suck, but I think with a little bit of cheating, you can understand where they're at. In blowing that up, this gauge was sitting here at 35. So just remember 35 represented the pressure drop between this return and the inside of the fan cabinet. That's the bad furnace. The good furnace showed up as 0.1. So he saved himself, whatever the difference is, I don't know what the math was on that, but a shitload of pressure drop, and he's going to have a filter now that lives because he's delivering the air square onto the filter. He's used a filter that's deep, and deep filters have lower restriction because there's more pleated more pleated media area for the same face. Beautiful thing. Okay, we got 20 minutes, I think we'll make it. Okay, well, we're crying on the shoulders of Richard Boucher. Richard Boucher used to run the Building Inspectors Association, BOABC. Richard's just a great guy. And Gary Milligan, I cheated. Went 2 slides ahead. Sorry. Branch duct issues. Okay, yes. If you choke a branch duct, Mrs. Smith is going to get ticked off because you won't get enough heating or cooling to a bedroom. But by and large, the equipment, his health is determined by the main trunks, supply and return. So in your mind, remember, there's 2 separate issues. Keep the equipment happy with trunk ducts. Keep Mrs. Smith happy with the branch ducts. But we have a problem right now if Mrs. Smith is too hot in summer, too cold winter, because we have no interior wall space to run ducts. We can't use exterior walls. The energy quotes essentially knock that down. Branch ducts are undersized. Branch ducts are too long. Branch ducts have too many fittings. We can't put equipment in the attic. And by and large, however, the equipment doesn't care. But Mrs. Smith does. So let's take a look at branch ducts. We were in Fairmont, in Kimberly. Gary Milligan ended up there doing a brief presentation to the building officials to try to make them a bit more aware of mechanical systems. And we're talking to Richard Boucher about the problems we have right now with interior designers leaving us no space at all for ductwork between the basement and the top floor. And Richard said, well, you know something? You should hit up the HPO. They'll fund you for some research. Absolutely blew us away. We'd never gone after that before. Don't know if it would again, but we were treated well. But this time when we put together a committee to look at that, we didn't go to the academic community. We said, let's take a look at some people that are real. So we got 2 Red Seal sheet metal workers. Gary Milligan's an A-fitter. Loris is an excellent draftsman from Echo Manufacturing. Loris Christian here, he's a professional engineer. He runs Echo Manufacturing. So he delivered an entire pickup truck full of all the branch fittings we could possibly use in a furnace to Don McAdams' home in North Vancouver. And he spent the whole friggin' summer finding out how do you get air from a crawl space to a basement. Because you can't get that information in regular tables, because you probably don't know, but oval fittings today are made with one rule only. What can we get it out of the door for with the least metal and the cheapest price? There are no standards. Here's something that'll blow you away. We're talking branch ducts right now. So these are what we call equivalent. And equivalent is a very special word in our language. Equivalent means the air is going from point A to point B, and it doesn't care whether it goes through a round duct, rectangular duct, triangular duct, whatever. If the duct is the same equivalent size, the pressure is the same for the same volume. Well, what we used to do in houses years ago, we used 3x10 duct because it was equivalent to 6-inch round. And I should mention, round duct is very, very magical in our business. Round duct has the greatest enclosed square inches for the least wetted area, meaning it's aerodynamic perfection because you've enclosed the maximum possible square inches through which you can move air with the least frictional surfaces around the edge. So in our business, everything is compared to what it would have been round. So you start all your designs with round, and then you go to square, rectangle, whatever space you've left to deal with. So if you've got to shrink it to 8 feet, you've got to start going out. And you're losing aerodynamic perfection, so you have to compensate 10, 20, 30, 40, 50% to compensate when you ask for reduced drops. But you have to use an 8-inch oval, which goes all the way to 11 by 3 to make it equivalent. The comparison that I like, however, is more powerful. If I take this 6-inch duct and I oval it, I can oval it 2 ways. I can stomp on it myself, or Echo will stomp on it for me and deliver it as an oval. The problem, however, to the trade is that we have 6-inch round ducts. Let's see, it says 6-inch, 30 gauge. Here it says 6-inch, 30 gauge. Guess what? It ain't the same thing. This thing here is 5-inch equivalent and flows 30% less air, and yet you look at the label and it's supposed to be the same thing, which is, of course, a complete crock. Let's look at the physics of this really carefully. It's kind of interesting when you look at it in detail. A 6-inch round duct has a 19-inch perimeter. That's how much metal it takes to make it. It's got 28.25 square inches. It's 6 inches round, and its diameter equivalent, of course, no surprise, is 6 inch. If I take that and I flat oval it, you're going to end up with the same amount of metal, and you're somewhere around 21 square inches of area. And that by itself would tell you that my area is equivalent to having a duct that's 5.2 inches, but an oval is not aerodynamically as beautiful as a circle, so it actually degrades again because the edges of the oval don't work as well as the center, so you've lost a full inch of diameter. So your 6-inch oval ain't. And that isn't even the beginning of the fiasco that we bring to you today. If you had your choice and you went from a crawl space to the upper level, you use 6-inch round duct, you go up 6 inch and you go over. And the standard advice for this is, well, it's about 10 feet for an elbow, 10 feet for this distance. In fact, Don McAdams' testing verified that the old tables that we've used aren't too far off. 6-inch duct, a couple feet here just to get air straight, a couple feet there, and this distance was 34 feet equivalent. That would be the ideal way of getting from a crawl space up to the bedroom joist system to get air to Mrs. Smith's bedroom. The next best thing we can do is go back what we did 30 years ago and use 3x10 duct, and that's 41 feet. There is a penalty, but not much. This is my favorite. If you use an oval duct and you use a round to oval fitting, and you go up the wall over 3x8, you now have 149 feet of equivalent length. So what you could have done in 34 feet now has gone up by 5 times. And we're treating this an equivalent in our business. So if you think you got problems with heating and cooling the top floor, it's only going to get worse in heating if you build tighter than you are today. And it's only going to get worse if you have designs that give you west exposure and sunlight and heat gain in the summer. Because I know there's a bunch of people today that were boiling their brains out, and our contractor customers weren't able to keep up with the cooling requirements in front of them. Unlike most studies, which are paid to do research, you have a 100-page report. You know the old thing in school is the report that's worth the most is the one that goes down the stairs the furthest. Well, we summarized this entire year's work in 1 page because we knew anything more than that was complete bullshit. So what we did is we took 10 different designs, of which there's a whole bunch of variations of 16 different methods of doing things, which got clicked off, and we're able to assign exactly how each of these things perform, so without any guesswork today, you know exactly how well this air is going to flow through the ductwork system. From your point of view, however, I can leave you with one take-home. The original fitting, which is number 1, had 34 fitting equivalent length, and it's equivalent to 0.9 fittings. The elbows are so free-flowing, we don't even count them as a whole fitting, and Jason will talk this afternoon about an elbow is only half a fitting. But if you use that fitting that I call the peg, it's 4.2 fittings, which means that if you use this versus this, you're adding 3 fittings difference. And a fitting in our business defines any time you change the direction of air. In houses, the straight duct is so short that the fittings dominate pressure drop, of course, plus filters. So anytime you have a change of direction, that furnace feels it. Here's the problem. If you had a simple house with 4 changes of direction here normally, and you went with 3 more fittings, you've ended up with a loss of 29% performance on a 4, 31, 25, and 44%. So just for round numbers, say you've lost a third of your flow when you've done that. These aren't negotiable. These are facts. These are tested. They're real. This goes on a lot in our business. People think this doesn't cost them at all when you put small duct into a big duct with a step. Huge pressure losses doing that, although it's not intuitive that that would occur. There's a bit of a recognition that the reducer will cause a restriction, but they're both equally damaging. We should be using tapers instead of sharp throat fittings. Okay, so we now understand what keeps the equipment happy. We understand what keeps Mrs. Smith happy, which is branch sizing. Let's look at leakage. Leakage is a big, huge issue. That's all I can say. About 10 years ago, we bought a theatrical smoke generator because we were using it for testing ventilation systems. We have a hell of a lot of fun with that thing. But we're too stupid to know what to do with it, so it sat on the shelf for 5 years, and we didn't know it. And finally, we ended up with some bad systems. We took it out and actually used it on a house, and it was just a wonderful, wonderful training aid. So what you do is you take a ventilation system, you pressurize it, close up the openings, you put smoke into it, and absolutely amazing what you can learn from it. It's just a super tool. Now, if I don't screw this up, this should work. But what I'd like to do is show you what happens when you put a smoke generator on this here elbow. It's 8 seconds. What we learned in this game is that once you have leaky ductwork, you can fill up a whole house with smoke. In fact, once before we had the smoke generator, we used smoke bombs, and we thought someone was going to call the fire department. Smoke was just billowing out of the top floor. The theatrical smoke generator is a little bit more civil. But the bottom line is right now, if you are putting in a heating and ventilating system and you're starting to approach more correct sizing, you really, really, really have to start sealing up your ductwork. It's non-negotiable. Unfortunately, the Canadian perspective is ductwork doesn't matter because we traditionally kept our duct in conditioned space. That's the Canadian answer, and that comes from the National Research Council, and the code has never done anything about this, although just laterally 936 has touched on it, but it's a pretty weak issue. The real answer is air does carry. As soon as you start choosing equipment and sizing the duct properly, you better start looking at leakage, or you're going to end up with Mrs. Smith not getting sufficient conditioned air to the bedroom. If you care about heating and cooling specific rooms, or you care about the cost of electricity, because 10% leakage is 31% increase in the cost of air movement. That's my whole message. I've got one last closing slide. Is anyone here an aircraft pilot? Single engine pilot certification? You won't understand the significance of the next slide, but I thought I'd try it anyway. Does anyone know what you're looking at?
Wingtip vortices.
Pardon?
Wingtip vortices.
If you are a pilot of a small airplane and you land in that airport or take off in that airport, within 10 minutes of that occurring, you're dead. Just because you can't see what happens to how air moves doesn't matter, it's not happening. What I've presented you today is very, very, very simple physics. It's 80 years old. There's nothing new under the sun. And we're going to do our best to bring this to our trade. We have over 100 people through this course already. I've condensed in 60 minutes what takes us 18 hours to convey in a proper fashion. All that I can ask is you leave your course here today and give a little bit more thought to the mechanical that you got going into your houses, unless you're building spec and don't care. Basically, that plane, when it takes off, is 1 million pounds. There's a vacuum on the wing, there's high pressure underneath, and the wingtip vortices right now will guarantee that anyone in the light plane underneath will be pounded into that pavement so fast that he'll kill himself. That's going on in all of our residential ductwork. It's only when you get slides like this that you can start to see what's really happening. And with that, thank you very much for your patience. My opportunity to soapbox. I welcome any flack and abuse you may wish. And I have to turn this watch in exactly 7 minutes. And you have 7 minutes I've left for you to abuse me.
Can I ask you a question? Why have you gone to PVC instead of sheet metal?
That's real easy. We did PVC ductwork and ventilation when we're trying to just problem solve and experiment. Number one, the PVC duct is cheap. The fittings will break the bank. And number two, we got royally burned. We used a duct system like that with ventilation on a house in Wellington Avenue. Beautiful, beautiful house, put in all together with a sheet metal contractor. But we ended up with, and we don't fully understand the physics, but the carbon black that's in our city air charged going through the ducts and it's stained the shit out of the ceiling all around the ventilation grills. I don't know the physics of it, but the particles of carbon black, which are very, very small respirable particles, got charged going through that duct. And when it came out of the ceiling supply grills, the Coanda effect had to stick to the ceiling, and the particles appeared to be far worse than it would have if it was a grounded sheet metal system. That's the only answer I can give you. The economics were not there, and the downside of the staining was the icing that broke the camel. Yes, sir?
How do you recommend ceiling joints and so on seen tape, but I've also seen that liquid stuff. I'm not totally.
Okay. There's a bunch of different ways you can seal duct. One, you can use duct tape, and that's how they built that Beaver aircraft. Duct tape is good for about a year. In the Canadian standard under which duct tape is made, it's a fire and smoke standard. It's fire combustibility and flame spread. It has no standard, no rating in the system for longevity. We recommend only two things: either foil tape, which has got an acrylic adhesive. Hello, Terry. Welcome to Vancouver. Welcome back to Vancouver. Your next speaker.
David?
Yes. I do know that. Some gentleman was kind enough to lend me his watch. And duct seal. And duct seal is excellent. They both have pros and cons, but they both will stay there. Duct seal has some weakness if the duct is jarred afterwards because it can crack off. The foil tape is very, very good, but it takes a lot of work to get it to properly adhere and to finger out all the little wee crinkles so it actually seals. Both will give excellent results under test. Any other questions? Terry, you will be covering makeup air this afternoon. There was a question to do with makeup air, when you need it, when you don't, all the intricacies. Any other questions, or you guys want to be first at the trough? First at the trough wins. Get out of here.